Hello guys, let's now solve this example problem uh, in application for the brace frame analysis we have discussed on the previous video. So in this particular problem, the uh, analysis result for the uh, load combination, dead and live load were given, no? Particularly on the brace column that is considered here, which is a part, of course, of a full frame. Okay, so this is a brace column, which is a part of a brace frame. So the loads that are considered are actually dead and live loads. So if this particular frame has no lateral translation, then we only become interested on the determination of the B1 magnification factor. Okay, since there is no lateral translation involved. So the properties of the steel is A572 with a yield strength of 50 ksi. So the flexural rigidity are not reduced, and also the effective length factor assumed to be equivalent to 1.0. Um, so I just made a definition of all these values here for me to be able to readily and accurately compute the needed parameters later. So also the properties are shown here, which of course are obtained from table, and the general solution for this is involves only actually 4 to 5 steps, in which the first step is more on based on the summary of the analysis results in terms of the dead and the live load. Okay, so I'm focusing on the LRFD method, and we'll just try to make a comparison between ASD, the some variations on the procedure after we solve this problem. So if we compute for the factor load combination 2, which is actually this 1.2 dead and 1.6 live, we will obtain the factored values of your loads and moments as shown here in the computation. Okay, so we have your load to be in kip, your moment here to be in foot kip. Okay, so or kip foot. So you can interchange it. Of course, when we talk of the bigger moment, which is M2 factor, this is the one we will be uh, magnifying later, because this is not yet the magnified MMT. So we will be considering the bigger moment, okay, which is 82.4 kip foot, to be the unmagnified moment MMT that we're going to use for our magnification process. So the factor forces are now shown, and the moment values at quarter points were computed by simple proportions. No? So this is now the summary of the moments and loads that I have computed, applying it on the particular column to be considered. So the use of getting the moments at the quarter points here is for us to be able to solve later the value of CV using equation of the AISC 1993. Okay, and these values are readily computed by simple proportioning, wherein if I just want to look into a linear proportion, if I have here an M1 value and M2 there, so these values here are simply proportional to the distances. Okay, okay, so if this is an L distance, this is L over 4, this is L over 4, L over 4, and L over 4. Okay, so I just make use of a triangular proportion to get this value MA, so simply it's equal to M1 plus the slope. Okay, the slope of this is simply M2 minus M1 divided by L. Okay, so if M2 minus M1 divided by L, and I multiply it by the distance, say this is my XA, okay, this is my XB, okay, and this is my XC here, and this is my, okay, so I don't need that because we only have to get the moments at the quarter points. So for your XA, this is simply 1/4 of L. That's why the L there cancels. So this will no longer have an L here. Okay, so if I put an L here and then I multiply this by L, I simply cancel those L's. So I don't need to write them actually. But if you want to write them down here like this, so it will just be the same. So by simple proportion, we can now get the moments at MA, which is 73.7, MB 76.6, and MC 79.5. So for the second step or procedure, so we need to compute the column strength moment, assuming there is no local backlink. And eventually, the reason why we can readily assume that there's no local backlink because we're using here a roll shape section wherein the values of lambda r to consider on the non-compact limit. Okay, so we know that lambda r is a non-compact limit, is assured not to be exceeded in this case. So lambda r is not exceeded. But if you want to make sure that there's no local backlink, or maybe the problem states that you have to check local backlink failure or condition, so you need to solve and compare your lambda. Okay, so your lambda uh, flange and the lambda, okay, lambda flange and lambda web with that of the lambda r flange and the lambda r web. Okay, so in case we have concluded that this has no local backlink, we can then now proceed with the checking of the weak axis. So this is now your weak axis slenderness, okay, ratio. So this is slenderness, a ratio of the weak axis Ry. So this is actually Ky L over Ry. Fortunately, your Ky and Kx are just, I think, the same. I think they are just the same as 1. So just take note of the error in the subscript there. This is a Ky all over Ry, L. I multiplied by 12 to convert it into inches. Okay? And then compare it with your CC requirement. So this is now your CC requirement equivalent to 4.71 square root of E over Fy 113.342. Okay, so this CC requirement is actually on the LRFD range. Okay, so in the ASD range, your CC is not exactly the same with this formula. Okay, so compare this to be less than this one here. Our conclusion is that we have here an inelastic buckling uh, failure. Okay, so take note that if we look into the beam uh, moment strength curve, okay, so if we consider the moment versus the strength relationship, okay, m over lambda here, so sorry, I'm talking of a column strength curve. So this is an FCR over, uh, let's choose a KL over R, okay? So this is shape is somehow like this, okay? So take note that this is the inelastic buckling region, and this is the elastic buckling region, okay? So the separation between the two simply is this 113.432. Okay, so we fell on somewhere in 55.629 here. Okay, so this value here of your FCR now, okay, becomes this one. Okay, so this is the inelastic buckling formula. So this 0.658 raised to Fy over Fe, which is equivalent to your lambda c squared, okay? Times Fy is equal to 39.875. So in the book, normally these are just computed on the basis of column load tables. That's why you cannot see the computation, the solution. But here I made the point that these are computed directly using the formula we have derived on our column strength concept. And finally, your VCPN now becomes FCRAG times VC, where VC is 0.9. So we get a 685.454 keeps capacity for that particular column. Taking note that if we check now the ratio between PU over PCPN, which is 0.63 and this is greater than 0.23, the column actually behaves more of a column rather than the beam. Okay, so the beam column behaves more of a column uh, than a beam. So in our interaction diagram, we will be reducing the bending moment later by a factor 8 over 9, as we have discussed on our beam column concept. Okay, for the beam strength, this is now a beam analysis considering the in-plane bending uh, scenario. No? So we have here now the properties as I have uh, obtained from table. Okay, and the plastic moment capacity, which I computed on the basis of kip foot and kip inch by simply multiplying my zx to fy. Okay, fy is defined to be 50 ksi a while ago. So my first step for a beam strength problem is to check for compactness. So here you need to check for compactness. Although for beams, we are assured for rolled shapes that your web are compact. But in the flange, there's no assurance, so we need to check. So your BF over 2TF now from the table is 9.92, and from our AISC code, this is 0.38 square root of E over Fy, which is 9.152. So take a look that there's a slight, okay, uh, uh, difference between the value of your actual width to thickness ratio, and this is actually a partially compact case for your flange. So this is your flange requirement. But for the web, it's actually very far, no? So for the web, it is a compact scenario. So what are we going to do? So the conclusion is we have a partially compact section. Since one element is partially compact, then we go to the interpolation formula that we discussed in our beam concept, wherein Mn is simply a linear interpolation of this formula or the graph into which you have, okay, so this is now the boundary for your lambda p and the boundary for your lambda r. So we need to make use of an Arratian proportion and the value of Mn in this regard. So if your lambda falls in between, okay, as can be seen here, the lambda p is in between lambda pf and lambda r. So our value here, Mn, is given by this interpolative formula. And computing it, we now have a value less than the plastic moment, therefore this is valid. Okay, for the lateral torsional backlink, we need first to compute for the CB formula or the CB value using the formula 1993. And what I did was I only plugged in the values I obtained a while ago here, okay, here. So this is my maximum moment. So this is my M max, which is actually equivalent to M2, okay? And these are my MA, MB, and MC, okay? A, B, C. So notice that these are now the value of my CB, after which I need to check for the LP and LR requirement on the basis of these two formulas. So I need some additional, these are additional properties, RTS, to be used on this formula. Of course, J, S, X, H, O are also computed here. Okay. Uh, okay. So J are actually given here, and also your H. Okay, it's computed here. RTS computed. C is automatically equal to 1 for what? For doubly symmetric shapes. Okay? So we studied all of this in our previous lecture. So just plugging in all the values and taking note that our LB is actually 1/68 inch. We take note that this is very big. Okay? And therefore, your LB is again in between, okay, in between these two values, having your value LP less than LB less than LR. So again, we need an interpolative uh, formula, okay, wherein again this is now my LP, this is my LR, and the value of LB is somewhere here, so I get the MN here. So by interpolation, taking note that CB is present there, I got 427.157, but this is greater than what I got a while ago from your value of MP, which is 403.33. Therefore, this cannot be a good value. Hence, I use MN on the basis of compact requirement, okay? Not on the LTB requirement. And multiplying this value with 0.9, I get my capacity to be 356.194 cubic foot. So I have now my capacities, okay, strength and capacities together with the loads. Okay, I now need my amplification factor for me to be able to compute for the magnified moment MR or the amplified moment MR, which is actually equal to your MU design. Okay, so this will be equivalent to the MU that you're going to use in your design. Okay, so first we compute for your Euler buckling load, a PE1. So PE1 means that this has something to do with the bending about, okay, the bending plane. So it has nothing to do with the weak and the strong axis. It has something to do with the plane of bending into which your frame structure was taken. Okay, so if I have here my frame example, for example, so my plane of reference is this one. So my bending here will be an in-plane bending, and as discussed earlier on our problem, so we have actually considered the strong axis as the axis of bending. Okay, therefore, this is an X. Always a strong axis is the IX and RX, KX. Okay, so we note that if we have a wide flange section like this, always the strong axis is the X-axis. Therefore, we place the X-axis along with the axis of bending to resist more the loads coming from the given forces. So Cm is computed on the basis of the formula of the AISC, where M1U over M2U again is taken to be positive, okay, bending moment sign, positive for single curvature. So since this is single curvature, okay, so this is single curvature, so this must be positive. If you use the other formula, some books uses negative. You use the sign convention on the rotational aspect, not on the bending moment sign. Okay. Okay. So it will just give you the same value for your CM, of course. So this is 0.944. Always this must be less than 1 for brace frame. Therefore, B1 is equal to CM all over 1 minus P over PU1, where PU here is the PU that we have computed a while ago here. Okay, so we have, yes, here. PU is this value here, okay? It's the actual value of 420 kip. And PE1 is this Euler buckling load along the bending plane. So I have 1.023 as my B1, and taking note that my general formula is MU-B1-MNT plus B2-MLT, but MLT is 0 because there's no lateral translation. Therefore, I don't need to get B2. B2 is irrelevant, hence MU is equal to B1 times MNT, and this is equivalent to 84.311. Applying the AIS equation, H1 dash 1A, or the formula I gave you on my first lecture, wherein if this is your value of P over PCPN of 0.633 is greater than 0.20, then I have to reduce, okay, the value of the bending moment, MU amplified. So, okay, so this is now an amplified moment. I have to reduce it by 8 over 9 and then divide it by the moment strength 3 and compute it on the basis of the bending strength a while ago, which is 356.194, and I get a value less than 1.0. Therefore, my sectional design is okay, using the interaction equation formula based on the concepts we have developed together with the limitations provided by the AISC code uh, that you have learned in the previous lecture. Okay, so thank you for listening. I hope you have learned how the procedure works for brace frame. So in the next video, we will be talking about the unbrace frame or sway frame to give you a better understanding on how they work or how they are applied to actual design and analysis problem. Have a nice day.